Welcome. This presentation is about machine learning-based prediction of imidazole derivative corrosion inhibitor efficiencies in mild steel using chemical descriptors. With a large number of potential organic compounds that can be tested for corrosion inhibition, experimental approaches alone may not be enough to screen them. Through machine learning, we can hasten the process and eventually save time and resources. Let us first discuss what machine learning is. Machine learning is a subset of AI in which we allow a machine to learn from data without being explicitly programmed. There are two approaches to machine learning, supervised and unsupervised. Unstructured or raw data can benefit from unsupervised learning where clustering, association, and dimensionality reduction is needed. In supervised learning, a machine learns from labeled data assigned by the user for classification and regression tasks. In the context of our study, we aim to predict inhibition efficiencies from different imidazole derivatives, which is a regression task. To do this, each compound should be described by inputs in which a machine can understand and have a relationship on our target variable, which are called descriptors. A descriptor is a numerical representation of a specific chemical characteristic of a given compound. Using irrelevant features may degrade the predictive ability of a machine learning model. Hence, the selection of important features or descriptors related to a target variable, which is the inhibition efficiency, is crucial in training predictive models. Since corrosion inhibition is mainly determined by molecule-to-metal surface adsorption, descriptors relating to it are considered to be relevant and are used in building the models. Listed here are the descriptors used in this study: ionization potential, electron affinity, HL gap, electronegativity, chemical hardness, electrophilicity, and electron charge transfer describe the electron transfer capacity and susceptibility of a molecule to and from a metal surface. Dipole and polarizability describes the total dipole moment and the electron density tendency for distortion upon metal surface contact, respectively. Hydrophobicity and solubility are also considered factors in molecules where aggregation forms a protective layer for a metal surface. The spatial extent of a molecule is also quantified through surface area and volume to describe the degree of coverage of a molecule that can potentially cover a metal surface. The models used in this study are random forest and XGBoost. A random forest model consists of multiple decision trees where specific decision is based on inputs. A majority decision becomes the final decision or a regression result from all the decision trees in the forest. Similarly, XGBoost is also tree-based. However, XGBoost employs a boosting method where trees are built sequentially from multiple weak models. The methodology consists of 5 steps: data gathering, pre-processing, model training and validation, model testing, and feature importance interpretation. 20 imidazole derivatives are gathered from literature and 3D modeled using Avogadro. The descriptors mentioned earlier are calculated from PM6D3H4 semi-empirical method. Other descriptors are calculated from RDKit, Mordred, and Data Warrior libraries and were arranged as structured data. The compounds are then split to training and validation and testing data: 16 for training validation and 4 for held out test data. Machine learning models are prone to overfitting, where a model simply memorizes the training data and performs poorly on the unknown test data. To prevent this, leave one out cross-validation was done, in which each compound is given the chance to be in the validation data. The hyperparameters of the model are also tuned during this process through multiple iterations. The model with lowest mean RMSE scores are then used as final models for testing. 4 compounds unknown to the model are then tested, and here are the results. For both models, i.e. predictions from the test data, shown in orange dots, are close to the actual experimental values based on the regression metrics. Feature importance is also done for both of the models to determine which features or descriptors are often used to make predictions. For random forest, polarizability, charge transfer, and molecular surface area are frequently used. Similar levels are also observed in XGBoost with solvent accessible surface area with the most frequently used descriptor. To summarize, robust models can be built from chemical descriptors for corrosion inhibition efficiency prediction. The models can be used to screen potential novel imidazole derivatives to save time and resource. Feature importance results may provide interpretability on corrosion inhibition mechanism in mild steel for imidazole derivatives. Finally, here are the references used in this presentation. Thank you for listening.